Good afternoon to everyone and welcome to this week's seminar. Our speaker today is Burcu Gülmez Temür, where she studied her undergrad, master's and PhD studies here in METU, her PhD under the supervision of Feridun Spudar, and she works at Atılım University ever since. So she has been working on permutation polynomials since a while, and this talk will be about her recent works on permutation polynomials. As you know, I mean, permutation, determining conditions of whether a polynomial is a permutation or a finite field is an important mathematical problem, as well as permutation polynomials clearly have applications in cryptography. So today, Burcu will talk about certain classifications and certain conditions on certain polynomials that produce permutation and complete permutation polynomials over finite fields. Thank you.
Thank you very much for inviting me. As Buket said, I will talk about our recent results. The first two are with Pınar Ongan. She was a PhD student here. The third one is with Pınar Ongan and Yıldırım Akbal. The other three are with Feridun Özbudak. And first, let me go on with the definition of a permutation. First of all, let me define this polynomial. If you look at this polynomial, this is somewhat special. Here, L divided Q minus 1. The polynomial is over FQ. If you have a polynomial of this form, it is called the nth order cyclotomic polynomial of index L over FQ. And if you have a monic polynomial of degree D, where D is in between 1 and Q, and moreover, if f is 0 at 0, then every polynomial can be written of this form. Now, let me define simply what a permutation polynomial is. Its definition is very simple. A polynomial is called a permutation polynomial. We abbreviate it as PP of the finite field FQ. Its associated mapping is bijective. And moreover, if both f of x and f of x plus x are permutation polynomials at the same time, then we call it a complete permutation polynomial. Now, the first question, the simplest question you can ask is, for which values of a can this monomial be a permutation polynomial? The answer is quite easy. It becomes a permutation polynomial if and only if D and Q minus 1 are relatively prime. And moreover, if you have the monomial x to the power D, where it's a permutation polynomial of FQ, then every constant multiple of it will be a permutation polynomial for every non-zero a in FQ. And if you ask for which values of a times x to the power p to the power r becomes a complete permutation polynomial, I mean itself and plus x must be permutation polynomial. It is again easy, the conditions are easy. A must be in FQ to the power n star, p to the power r, q to the power n minus 1 must be relatively prime, minus a inverse must not be a pr minus 1 first power in FQ to the power n. And the first problem we worked on was this one. There are many mathematicians who studied on this polynomial. For which values of p, the question is, for which values of p in FQ to the power n star, f of x becomes a permutation polynomial, and moreover, for which b it becomes a complete permutation polynomial. This was the first question. Now, in a paper of Wang, we have seen this polynomial. It looks complicated, but it is not actually. Wang gave the conditions for this polynomial to be a permutation polynomial, and he has a corollary. This polynomial of this form is a permutation polynomial if and only if these two conditions in I and 2i happens. This is if and only if, and moreover, you can find the inverse of this polynomial. And here the coefficients are like this. Using this idea, we asked whether we can write our polynomial in the form of p of x. This was the first question we asked. I mean, is it possible to write polynomials? We are asking also the question when f becomes a complete permutation polynomial also. So is it possible to write f of x and f of x plus x in the form of p? I have shown you before. And unfortunately, we couldn't find a positive answer. Instead, we couldn't find the b's for which f of x is a permutation polynomial, but instead we find when it will be a permutation polynomial if b is not this. Okay, so this is not a very good result actually. And similarly, we have found also if b is not this and this, then it's a complete permutation polynomial.
Can I ask a question?
Of course.
It's finding the condition that if b is not equal to something, doesn't the answer?
Yes, but not exactly. You cannot write b is equal to this exactly. So it's not a very good answer. Yeah. So it's not a bad result, of course, but it's not good as we want. Because when you find the conditions when a polynomial is a permutation polynomial, you want to find for which b exactly, and we cannot answer this. Nereye basınca ne oluyor acaba?
Alttaki sağ sol.
Bu ileri gidiyor. Oh, okay. And we kept on looking at this polynomial where n is equal to 5 because we have seen in the literature that Vasilieva and Zinoviev answered the question for the case n is equal to 2 and n is equal to 3, and then Woolley, Heleset, and Zhang answered the question for the case n is equal to 4 where p is not 2. Vasilieva and Zinoviev answered the question for the case n is equal to 4, p is equal to 2. The question was not answered for the case n is equal to 5, and we were able to find the answer. And later, Bartoli et al. Answered the question for the case. Actually, this was before us, and n is equal to 5 was empty, but n is equal to 6 was found. And we were inspired by the work of Bartoli et al. And let me show what happens. This is a result of Bartoli. They say if n is odd and b is an fq to the power n star, and suppose q is greater than this number, then if this f is a permutation polynomial, then p divides n plus 1 over 2, and moreover, the trace of p is 0. And it has a corollary. We use this corollary actually. Let n be odd. Suppose q is greater than this huge number. If p is not 2, n is not congruent to 3 mod 4 or trace of p is non-zero, then f of x cannot be a complete permutation polynomial. So, şu an hatırlamıyorum gerçekten. Ama makaleyi söyleyebilirim. Okay, and then you substitute 5 instead of n in the corollary, you find that whenever q is greater than 114, this will not be a complete permutation polynomial of fq to the power 5. So we and this is the result of Z. We used this result actually. It says if you have such a polynomial, It's a permutation polynomial if and only if L and Q to the n minus 1 over Q minus 1 are relatively prime. And this polynomial, the product, is a permutation polynomial. And here Gx, G to the Q i's are obtained from Gx by just raising every coefficient of G to the Qj power, Qi power. Now for our case, n is equal to 5, we chose L is equal to 1 and Gx to be the polynomial x plus b of degree 1 for some b, and define the polynomial hb in this form by raising the coefficients of x plus b to the qi power. Then from the previous results, from the Ziv's result, we obtain the following corollary. Sorry. Then the result is this: the polynomial we are looking for is a permutation polynomial if and only if this HB is a permutation polynomial. So the question is somewhat simpler than the previous one because HB is just a degree 6 polynomial. So you can use some previous results. Here we used the idea. We defined lambda 1 up to lambda 5 in terms of b. You will see what happens here. Actually, the main idea here is we are looking for b for which h of h sub b is a permutation polynomial. So the idea was this: we have a notion of normalized permutation polynomials. I forgot to define it. And I also forgot the definition. Sorry. But if the idea is here, we have seen that in the literature, we have the complete list of normalized permutation polynomials of degree 6. And the idea was to just compare our polynomial with the list. And we did it. And we have seen that here, if HB is a permutation polynomial, we saw that it must satisfy these. This is the complete list. It's not a very huge list, as you see. And as a result, by comparing our polynomial with the normalized permutation polynomials list, we have seen that we have a permutation polynomial if and only if when Q is 11, lambda i's must satisfy these conditions, these 3 conditions. When Q is 9, we have these 4 conditions. When Q is 27, Q is 2 to the power m, Q is 8, Q is 16, and Q is 32. We found all the permutation polynomials. So if you go back to the corollary, these are the conditions for which HB is a permutation polynomial. So these are the conditions for B, for our F to be a permutation polynomial. So the question was completely answered by us. Then this is Ziv's lemma. This is very famous in this topic because it has been used by many researchers. It somewhat simplifies the study because instead of looking for F which permutes Fq to the power n, the big field, you just look at a polynomial which permutes m mu d, where mu d is the set of all elements which are roots of unity, which are d roots of unity. So the permuting set becomes very small compared to the big field Fq to the power n. But it looks simple, but in most of the cases, it is not so simple to show that a polynomial permutes mu d. And I will show you our first result on this. Here, this was a very simple result. We have seen in the literature that for this H, the polynomial of degree 5, we have seen that it is a permutation polynomial if characteristic of FQ is 2. Then the characteristic is even, it's a permutation polynomial. And we want to know whether it's a permutation polynomial for odd characteristic also. The answer was unfortunately no. It's not a permutation polynomial if Q is not of characteristic 2 and Q is not 4 modulo 5. And then I will show you the technique we used here. And then with Permutation, that we wanted to classify permutation polynomials of this form, where G is a polynomial of degree 3, but x squared is not there. And we have seen some results on this polynomial in the literature, but we have seen that the results are not complete. The results are not if and only if finite. And we wanted to complete this result, and we used Zev's lemma in order to do this. So first we need to find out find out B and C for which G does not have any roots in UQ plus 1. By UQ plus 1, I mean the Q plus first root of unity, the set of Q plus first roots of unity. So from the beginning, we assume that G of 1 and G of minus 1 are not 0. Otherwise, they will be roots because they are both in UQ plus 1. And we have first, we first found a proposition which shows the condition such that G has a root in UQ plus 1. We don't want it to have roots in UQ plus 1, so finding where it has a root is important. And we have seen that it ends up like this. When the characteristic is even, we have two conditions. When characteristic of FQ is odd, we have two conditions. These are the conditions for G to have a root in UQ plus 1, and we don't want these. And in the literature, there is a proposition in a paper by Bartoli and Coase. However, their result is only an existence result, and moreover, there are some polynomials such that they cannot show that they exist. So the proposition is complete in our case. And then here is the main idea. Now, first, suppose it has no roots in UQ plus 1. We already know the conditions for it to have no roots in UQ plus 1. And for any x in UQ plus 1, we can write x cubed times g x to the, here q minus 1 should be out of the parentheses in the first one. So I'm taking the power q minus first power of gx. Then I can write it as g of gx to the power q over gx. And by substituting 1 over x instead of x to the power q in every step, we end up with a rational function. And note that now the main idea is here. F of x permutes UQ plus 1 if and only if whenever f of x is different than f of y, x must be different than y. This is the definition of one-to-oneness. Everybody knows. So computing f of x minus f of y over x minus y, we end up with a curve, with an algebraic curve over fq. I guess it was fq square. Yes. Over fq square, we have two variable polynomial in fq square. So the question is actually here, are there any fq rational points, actually UQ plus 1 rational points, such that x is not equal to y? If the only points satisfying this curve are x is equal to y, then we are done. It will be 1 to 1. So we are looking for these conditions, but we realize that if we work it over uq plus 1, then the idea is this one actually. We look at the curve and then we consider all factorizations of it, all possible factorizations of it, and work on them case by case. But the problem is here, if you can work on the factorizations, all factorizations, except one of them. If the curve is absolutely irreducible, then you have no tool to answer the question because we are working over uq plus 1. But if we can find a way to take everything to fq instead of uq plus 1, then we will be able to use the well-known Hasse-Weil bound when the curve is absolutely reducible. This was the idea. We did not realize it at first, but then we realized it. Now, this is our first main result in this paper. Assume CF, the curve is not absolutely reducible. Then it's a permutation polynomial of fq square if and only if one of these two conditions hold. This is where the characteristic is even. And in the odd characteristic case, it's again CF is not absolutely reducible, then it's a permutation polynomial if and only if it satisfies one of these conditions. And these results were not, if and only if, and they were not complete in the paper I have talked about. And in the absolutely reducible case, by using the Hasse-Weil bound, we can show that it's not a permutation polynomial. So the question is complete in this case. Then we worked on some quadrinomials, on one quadrinomial actually. This was studied by Tu Zheng and Heleset, and later Tu Liu Zheng revisited these quadrinomials, and they solved the question when characteristic of fq is 2. And Li Q, Li Chen proved that the sufficient condition is also necessary. Thus, the even characteristic case was complete. And later in Gupta, in a paper, Gupta studied the permutation, the permutation properties of this polynomial when the characteristic is 3 or 5, and proposed some new classes of permutation quadrinomials like this. And we wanted to know whether we can solve the problem for all other odd characteristics other than 3 and 5. And here we start with this map. We first choose an arbitrary element which is in fq square but not in fq, and define a map phi of x plus z over x plus z to the power q, where phi takes infinity to 1. You can easily observe that this is a one-to-one function from fq union infinity to mu q plus 1. I have shown it here, but you can easily find it. And phi is then also onto. If it is one-to-one, it's also onto, because on both sides you have same number of elements. fq union infinity and mu q plus 1 have the same number of elements. Both have q plus 1 elements, so it's also onto. So we have a one-to-one and onto map from fq union infinity to mu q plus 1. Now the idea is, and we also, since it's a one-to-one and onto function, it has an inverse, naturally. And in this setting, we can say that f of x is one-to-one on mu q plus 1. This is the question we are trying to answer. And thus permutes mu q plus 1. This is the question in Ziv's lemma, the second condition. If we can answer it, we know when it's a permutation polynomial. instead of looking at F, you can look at phi inverse composition, F composition phi. Then what is the idea here? Instead of looking at the map from mu cube plus 1 to mu cube plus 1, instead of looking at F, you take everything to FQ union infinity and try to answer whether, try to find the conditions for which phi inverse F phi permutes FQ.
Hocam infinity neden ekledim?
Çünkü şeyde map'in kendisinde bir dakika. Yani, çünkü bir yandan şunu istiyorsun. Mu Q plus 1'da Q artı 1 eleman var. FQ'da Q eleman var. One to one bir map yazmaya çalışıyorum. Dolayısıyla yani one to one ve odd olmasını istiyorum. O yüzden eleman sayısını da eşitlemek istiyorum. Ve inverse'ine de bakarsanız zaten x eşittir 1'de problem var. Değil mi? Inverse'de payda da çünkü x eşittir 1. Phi inverse 1'i de sonsuz olarak tanımlarsam her şey halloluyor. Now, we choose also z in FQ square minus FQ suitably, so the computations become simpler. So we took everything from mu Q plus 1 to FQ. The question is phi, when phi inverse F phi is 1 to 1 on FQ, union infinity. So we wrote down, first of all, we have to again determine when this polynomial has roots in mu Q plus 1. Again, we excluded 1 and minus 1, otherwise it will have a root because 1 and minus 1 are both in FQ and mu Q plus 1. And we have found these conditions. It has a root in mu Q plus 1. Again, we didn't find the conditions for which it does not have a root. Instead, we found the conditions for which H has a root in mu Q plus 1. If and only if these three conditions are satisfied. The Q plus first roots of unities. The set of Q plus first roots of unity. And this is our first result when if Q is of odd characteristic, where 3 and Q minus 1 are relatively prime. This was the great common divisor condition comes from Zev's lemma, the first condition. And we here, when you write, I said we were writing a curve instead of writing f of x minus f of y over x minus y. This time we are writing it for, instead of f, we write phi inverse f phi, that composition. And when you write that curve, there are two cases. 3 minus 3c plus a minus b is 0 or not. This is the one with when it is 0. If characteristic is not 3, then it's a permutation polynomial if and only if a is 3c and b is 3. If characteristic is 3, then it's a permutation polynomial if and only if a over 2 minus c plus a is a square. Then we have in order to complete the case, we have to consider the case where 3 minus 3c plus a minus b is not 0. And we found that it's a permutation polynomial if and only if one of these conditions are satisfied. So we completed the case for odd characteristic. And as I said, it was already done for even characteristic. So the problem is completely solved. Later, we wanted to characterize permutation trinomials of this form. And in both even and odd cases. Actually, this one comes when you take one of the actual, I think, I don't remember it well, but if you take one of the coefficients of the quadrinomial in the previous case, as 0, then you obtain this permutation trinomial, and we have seen that in the literature it was not done, so we wanted to solve it in both even and odd characteristic cases. And again, we first find out the conditions where h of x has a root or does not have a root. This is the first proposition. Here we found when h has no roots, if and only if b is not 1 or b is 1, and we have two cases when characteristic is even and odd. Then, using the same idea, same curve idea, I mean, looking for the FQ rational points. Again, we have two cases. 3 plus a minus b must be 0 or non-zero. If it is 0, then we have this result. And it's if characteristic of FQ is not 3, then there are no such permutation polynomials. And if characteristic is 3, then it's a permutation polynomial if and only if a is equal to b and b over b minus 1 is a square in FQ. And the next one is when 3 plus a minus b is non-zero. In this case, it's a permutation polynomial if and only if one of these two conditions are satisfied. And we go on with the even characteristic case. It's a permutation polynomial if and only if one of these conditions hold. And we have, in this paper, we have another permutation trinomial. In a paper, Zahu and Fan determined the permutation polynomials of this form, where q is 2 to the power m, and they have seen that it is a permutation polynomial if and only if m is odd. Inspired by this result, we study a more general polynomial. We put coefficients in front of x to the 2q plus 1 and 3q, x to the 3q. And we want to complete the problem in both odd and even characteristic cases. And first, again, we have a case where 3 minus b minus 3c is 0. This comes from the curve. If it is 0, then there are no permutation polynomials in this form when FQ is of odd characteristic. When 3 minus b minus 3c is not 0, then it's a permutation polynomial if and only if one of these conditions holds. And in the even characteristic case, it's a permutation polynomial if and only if one of these conditions hold. So the problem is complete, and let me show you the well-known Hasse-Weil bound. We use the one given in the book of Hu, which is lectures on finite fields. It says if you have, first of all, a polynomial is absolutely reducible if it is irreducible in FQ of x0 up to xn. And if it's homogeneous, then we define Vp to the power n. And using this, you can write the Hasse-Weil bound in this form. If you have an absolutely reducible homogeneous polynomial of degree d over x, y, z, then this Vp square fq of f minus q is less than or equal to this number. Here Cd is a constant depending only on d, and moreover, it can be chosen as 1 over 2 times d minus 1 squared plus 1. And in all the absolutely reducible cases we have studied, we use this idea, and we in each case we have seen that there are no permutation polynomials when the curve is absolutely reducible. And there is also, since there are many papers on permutation polynomials, you can ask if there is an equivalence relation between some of the permutation polynomials or not? Can some of them be similar permutation polynomials? And we have a definition of quasi-multiplicative equivalence of two permutation polynomials. They are called quasi-multiplicative equivalent, FMG are called quasi-multiplicative equivalent if you can find an integer d in between 1 and q minus 1 with d relative prime with q minus 1, and if you can write f of x as a times g of c times x to the power d, where a and c are in fq star. Using this definition, in the last paper I talked about, we want to compare our results with the known permutation trinomials. This is the list of all known classes of permutation trinomials of the form of this form, of the similar form to ours. The last two are our results actually, and by using the quasi-multiplicative equivalence definition, we studied on this, and we have seen that f of x is not quasi-multiplicative equivalent to g1 if b and c are not both 1, and f of x, the other permutation polynomial, is not qm equivalent to gi of x, where I is in between 1 and 3. B and C are not both 1. Actually, when B and C are both 1, are the permutation polynomial that we started with. So there is no problem. This shows us that our results are new permutation polynomials, are not quasi-multiplicative equivalent. Okay, that's all. Thank you for listening. And let me show you some of my references.
Any questions?
You say algebraic curve, but I think is it the projection of the algebraic curve over the finite fields?
Somewhat, yes. Actually, we are not dealing with the algebraic curve properties. We are just looking for FQ rational points of it. So it is simple. We are looking whether that curve has roots, or let's not just say roots. Can you find x and y such that they satisfy the curve, but x is not equal to y? If you can find such points for the curve, then it will not be a permutation polynomial. If you just have the result that whenever the curve is 0, it results with x is equal to y, then you have a permutation polynomial. That's the idea. And for the absolutely reducible case only, where you see an algebraic curve really, we use the Hasse-Weil bound.
By the way, I don't understand the distinction between absolutely irreducible and irreducible.
Irreducible means, for instance, a polynomial can be irreducible over FQ, but it may not be reducible in FQ square. If it is absolutely irreducible, it is irreducible in any extension.
Oh, okay. And in which field of cryptography this subject is used?
I don't know. I'm not interested.
This was my desired answer because I'm more interested in mathematics part of it.
I don't know.
In Wikipedia, it says they're operating codes.
It has many applications in cryptography and coding theory. Actually, I have also written a chapter on it, but I don't remember anything. I'm sorry.
Around page 20, you define some constants like lambda I. They look like symmetric polynomials.
Page.
Around 20.
Do you mean these?
Yes. So are these related to symmetric polynomials? And do you use Colloquia to calculate
No.
coefficient?
No. That's not too complicated. We just, you can just find this idea in one of the papers. I guess it was in.
First one is like trace.
Yeah. Yeah.
And the last one is like norm.
Yeah.
So the intermediate terms are like the other coefficients.
But we did not do any Galois theory. It was not that complicated. We just wrote these and found and compared these with this list. And since you know the complete list of normalized permutation polynomials of degree 6, if our polynomial is not in this list, then it will not be a permutation polynomial. That the idea was simple there.
Here you also mentioned about some difficulty of the representation of the terms of grammar. Maybe to ask one question about the representation of this for you obtain the result and corollary, but it was not easy to represent in terms of grammar.
I did not understand. In which one?
You said that it wasn't a good result.
How? This one. I guess. Yeah. Because we cannot find exactly for which B it's a permutation polynomial. We can just tell that if B is not this, then it's a permutation polynomial.
So you find deciding whether B is in this form is another problem.
Yeah.
Did you attempt on this problem?
Yeah, and we couldn't solve it.
So my second question is, what's the importance of the integer 3 x cubed and q minus 1?
Actually, it makes the curve a simple one. When you multiply a degree 3 polynomial by a degree 3 power, when you write f of x minus f of y over x minus y, you get a curve of degree 4. And it is actually, let me show you that curve. I have written it in one of them. Here, you see it starts with x square, y square. And since it's of degree 4, you can have 3 plus 1 factorization, 2 plus 2 factorization, 1 plus 1 plus 1 factorization. But in 2 plus 2, you have 2 cases. So the number of cases of factorizations is not much. But nowadays we are working with a problem with Bouquet. Our curve starts with x to the 4, y to the 4 of degree 8, and we are thinking that we are crazy to work on this problem because there are so many cases, so many sub-cases. But in this one, you don't have much cases. You just have 2 plus 2, 3 plus 1 will factorize as degree 1 factors. I can assure you. 2 plus 2 factorizations have 2 forms. One of them is one curve starts with xy, the other xy. One starts with x squared, the other starts with y squared. You have 2 cases. And then you have just the linear factors and the absolutely reducible case, that's all. But when you work with a degree 8 curve, can you count number of possibilities?
All partitions.
That's why x cubed makes me to write such a curve here. And actually, we did not want x cubed, actually, but we have seen problems in the literature, open problems in the literature. And now I understand why they take x cubed.
Somehow it would mean x cubed is somehow shifting.
Yeah.
The shifting of the polynomial also q minus 1 in the evaluation of g, it's x to q minus 1. So can we replace Q minus 1 with another thing so the problem will be easier?
No, because this comes from Ziv's lemma. Let me show you once more. Here. You must take the q to the n minus 1 over d2. Actually, you can write, the answer is yes. You can write something different than q minus 1, but it must divide q to the n minus 1. There is only one paper I have seen in the literature where they take q plus 1 instead of q minus 1. It makes things easier. That's why all the problems are solved in binary case. You cannot find.
I was thinking, while you were presenting, I was thinking about binary case when it's easier, but when what prime case, whether it must be maybe good idea to make extension of the binary cases for all characteristics. Because in binary cases, 3 is just a quadratic polynomial. Quadratic polynomial is 2 minus 1 is maybe somehow inverse polynomial or doesn't correspond to inverse, then increase to something else. So those extensions will be considered for studying all prime cases.
Actually, the only open problem in characteristic 2 was this one. I guess it is still not solved if you want to attack. This one, when forget about n is equal to 5, this is not completely solved. This is completely solved for p is equal to 2. No, for n is equal to 4. So it is not completely solved.
N is equal to 4?
When n is 4 and p is 2, it is solved. But when you take for any n, if you attack this problem, it is not solved. And it seems very simple. It's just the binomial, but it's very hard to get the answer. Bir bakışmaya devam edeceğiz.
Pardon, işte korkuyor musun?
Ha, lütfen.
Yeah, this fx minus fy over x minus y. It reminds me of differentiation. Does the anything to do with it?
No. You just you remember the definition of a one-to-one function. If f of x is equal to f of y, then you want to end up with x is equal to y.
Yes.
That's why we are dividing by x minus y.
Are you interested in families of algebraic terms, or just one by one?
No, just
study them.
you just obtain one curve and you try to factorize it. You try to study on all possible factorizations and also the absolutely reducible case, and the problem is complete.
Maybe I thought that maybe solving part for one curve gives rise to the solution of families of other curves. Maybe some common problem.
Maybe I did not think about it. Maybe.
Any other questions? So let's thank our speaker again.